A stomp rocket is projected from the ground level in two different trials, with two different initial velocities. It was found that the total time the rocket stays in the air is t in the first trial and 2t in the second trial. What is the difference between the maximum heights in this experiment? Ignore air resistance. Okay, so the answer here is that the second one is going to go 4 times higher. But in order to explain this, I need some space. So I'm pushing all these answers aside. Okay, it's a little complicated when you think of the fact that they have different initial velocities. So what I'm going to do is I'm going to say let's just picture the stomp rockets falling from their maximum heights. That's going to take the launch velocity out of it, so we don't have to deal with it. So here, let's say that this is the, well, actually I'll draw it smaller. The trial 1 goes to this maximum height here, and this is height 1 for trial 1. It's going to fall from rest from the very top, right? We're talking about like the peak of the projectile right at the top here. It's going to fall for a certain amount of time. The amount of time that it falls is technically t over 2. That's the falling time because the total time was t. But what's really going to matter is the fact in the second trial it's twice that, but still. This one's going to fall a certain height, and it's going to take a certain amount of time to do that. The other one is going to fall a different height. I'll call that h2. And the fall time for this one is half of its total flight time, which is t. Now, we can relate height, the distance, the displacement, vertical displacement, with time with the second kinematics equation. The maximum height, or you could think of it like the change in y, is going to be, well, the second kinematics equation is x equals x naught plus v naught t plus 1/2 at squared. But since we're only worried about the part of the flight where it's falling from rest, that's going to help us get rid of that v naught t term. And we don't even care about the initial position. We just want to know that distance h. So h equals, all that really matters is the acceleration of the objects is the same, right? A is the same for both objects. So we have 1/2 at squared. This is the equation that we can use for both of these in order to compare max height with air time, because a is the same for both. Okay, so over here we have a max height. We have 1/2 a, which is 9.8, just little g, and the amount of time that it is falling was t over 2 squared. So we have 1/2 g, and now I'm going to separate these into 1/2. Here, I'm going to write it a little differently so that the algebra I'm about to do makes more sense. So instead of t over 2, let's make it 1/2 t squared. That's the same thing as t over 2 squared. 1/2 squared is 1/4 times t squared is t squared. Now, our original equation was 1/2 at squared. So therefore, this 1/4 is the thing that's going to come out front. We have 1/4 times 1/2 gt squared. Now let's go see what the other one looks like. This is h2, different height. This is the same, 1/2 g, but the flight time is t squared. So it's not t over 2, right? It's twice that amount of time. So therefore, we get 1/2 gt squared. Now look, 1/2 gt squared is right there. So therefore, the max height for 1 is 1/4 the max height of the second one. And if I erase all this and bring these back, you can see the maximum height for the second trial is 4 times greater, because based on the math I just did, trial 1 went to a height of 1/4 h, whereas trial 2 went to a height of h, 4 times greater. The answer is B.